Pay close attention. Are you ready? Goes something like this. Today, I'm going to teach set 96 and 97. I will not have any question time. I want you to check your 95 extra practice tomorrow on my website, or tonight on my website, turn in tomorrow. Okay? Are you with me? Cool. Friday, you will have, I will be absent. I am gone. That's why I'm teaching 2 today. You're going to do set 97. You'll have all day in class to work on it. Monday is, I am also gone, and you will have set, your homework on tonight is set 96. Okay? Monday I'm gone, and Monday you'll have 97 fun sheets to work on again in class. On Tuesday I'm back. All right? So that's the plan. You should be turning in, tomorrow you should turn in 95 extra practice and 96. Monday you should turn in 97. And on Tuesday, you'll turn in 97 fun sheet. Are you down? Hi, what the heck? Okay, here we go. So I'm going to do the notes for 96 really quick because it's review. So, let's go with, skip the first part of the notes of 96, which are pink, and go to this part. Just a review, and I'm talking fast. What's the key to taking the derivative of absolute value? Piecewise. Cool. I'm going to graph this to determine where it's positive, where it's negative. What does root 3 represent? The vertical shift, or the horizontal shift, or something else? Vertical shift. It's centered at root 3. And the amplitude is 2. Is 2 more than root 3, so that we'll duck below the axis, or 2 is less than root 3 and will always be positive? Alright, so it seems like with the positive sine curve, I would eventually get a little below the axis, but because of the absolute value, that part would be brought up. Yeah? Alright. Now, in order to write this piecewise, whether you know the graph or not, you need the zeros. So where is root 3 plus 2 sine of x equal to 0? Sine of x is negative root 3 over 2. Is that a pi over 3 or pi over, you said pi over 3. What quadrant is sine negative? Or quadrants is sine negative? 3 and 4. So what are the pi over 3's and 3 and 4? 4 pi over 3 and 5 pi over 3. All right, so writing f in a piecewise way, what's the first function? Opposite or same? Same. Root 3 plus 2 sine of x from where to where? From 0 to 4 pi over 3. Okay? What about the next region? From where to where? And opposite normal f, opposite f, or normal f? Opposite. Opposite of the first number, or both? Both. So root 3 minus 2 sine of x from 4 pi over 3 until 5 pi over 3. And finally, normal, back to normal, unflipped, root 3 plus 2 sine from 5 pi over 3 to 2 pi. Am I done? No. The question is find the derivative. So what's the derivative of the first branch? 2 cosine x. When I do the domain, is the derivative defined at 0? Still inclusive of 0? No. Did anything happen at 0 to make the derivative no good anymore? That's fine. So 0 is included. But what about 4 pi over 3? Not included now because there is a sharp turn. Do not include 4 pi over 3. What about the next branch's derivative? Negative 2 cosine of x from 4 pi over 3 to 5 pi over 3, not inclusive. And the final branch? 2 cosine of x, 5 pi over 3 to 2 pi inclusive of 2 pi? Yes. Okay. So it seems like so this is by far the common way to do absolute value derivatives is piecewise. It's the way they do it on the AP test. That's the way you should do it on the homework and the test. That said, there is a little known math kind of trick to doing absolute value derivatives. And it goes to something like this. Wouldn't you agree that the derivative is always kind of the same thing, 2 cosine of x, the normal derivative? The only question is it the opposite of the normal derivative or the normal derivative? Yeah? Now check this out. This is another way to say the derivative without piecewise. It's root 3 plus 2 sine over absolute value of root 3 plus 2 sine times 2 cosine. How does that work? It's pretty great, actually, yes. What does this do for? That's the derivative, okay? What is the first part do? Yeah, it's either 1 or negative 1. When the function is above the axis, what's the difference between these two? Are they exactly the same? When it's above the axis, it's positive. These are the same, and it's just 1. When it's below the axis, however, these have the same value, but the top is negative, the bottom's positive, and so this amounts to negative 1, or the opposite of the derivative in a negative situation. That is one way to do it, and I like it, but you're going to do it piecewise, okay? All right. I think this went pretty well, so I'm really sorry to leave you a bunch of blank notes, but we have integrated absolute value. It's piecewise again. You need to find the zeros. Do you want to practice that, or you feel okay? Okay. I want to focus on the harder stuff of the day, and that is 97. So I know that's a lot of blank notes, but 97 is the more conceptual part, and I want to err on the side of getting that done. While we do this, the seating chart is coming around. It's just for the attendance purposes for the sub. Keep in mind, this is oriented for the sub to read, so I understand you read this way, but she's reading it this way. So put your name the right direction. I put a few down just for varying purposes. Put your name down, pass it on. Okay. Now, today is a totally different kind of volume. It's not a revolutionary volume. It's more of a cross-section volume. Cool, you'll love it. And we're going to start by practicing left-hand graphing method. So, would you draw for me an x-axis? Okay? Now I'd like you to draw a y-axis at a slant, like this. Now if I were so inclined and I wanted to do 3D calculus, this on a left-hand graphing method is the z-axis. And out here is the first octant in here. If I were to graph the square root function from 0 to 4 in 3 space, then would you, oops, I'm going to put these tick marks a little more evenly spaced. Would you put 4 tick marks on x and 2 tick marks on y? And we're going to locate the endpoint when x is 4, y is 2. Now the temptation is because you're in such a habit of, all right, to get 2, I just go up 2 in a totally perpendicular way to the x-axis. You don't do that. You go parallel to the y. So you're going to, when you go up 2, it has to be 2 parallel to the y-axis. So here is 4, 2. Yeah? And the square root graph should look something like that. so that almost as if you put it on a paper, but then looked at it at an angle or from perspective. You with me? Okay, we're gonna be really doing some cool drawings. You're gonna love this if you're artistically inclined, and even if you're not, with practice you can get good at these. They do inform you, you do need to draw the picture. So, here's the deal. Rather than a revolution, taking this and rotating it about an axis, and because that distance stays the same as you revolve it, you have all these discs or circles or washers, and you see pi. We're not doing anything like that. Now, I'm going to pretend like that's a plot of land off which I build. The building will involve cross sections or lots of slices. So let's go to one example here. Would you give me that same drawing? An x-axis like you normally would draw it, with a y-axis at a slant. Don't worry about the z this time. Give me 1, 2, 3, 4 units in x and 2 units in y. And then locate for 2, which should be parallel to the y-axis, so also slanted, and draw the square root graph. Once you get that, then we'll move on. Okay, so now, the idea here is we're going to get a three-dimensional figure by stacking stuff on that plot of land. What we're going to stack is square cross-sections parallel to the y-axis. Let's first draw a few slices parallel to the y-axis. So here's one parallel to the y-axis. Those are parallel to the y-axis. Not as using the whole numbers, but they could be at the halves or any number. All right, now here's the 3D part. The cross sections are coming up out of the plane, and they're squares with the base here, and so the height, remember when we did the z-axis, it was straight up and down, yeah? So when you draw the height of the square, it should be exactly as long as the base was. So imagine how long that is, and that's how high you're going to draw straight up and tap it up. Likewise here, this one at 2, it's going to now be a little longer. Tap it up. And this is a little longer. And even longer. Now, if you think about those slices and all the slices in between and connect the corners, if you connect the corners down to where they reach nothing, and they would gradually go to nothing. And likewise, the far corners would go down to nothing. Now, that's pretty cool. I love to see it, but it's not drawing class, it's calculus class. So what do you reckon we're going to do? We're going to find the volume. Okay? All right. Now, for all of these, all of these problems today are all volume is the sum of many slices. The slices could be lots of different geometric shapes. They could be squares. They could be triangles. They could be semicircles. And they don't even have to be oriented that way. They could be oriented this way. Okay? Now we will do all of those in the next half hour. So, here we go. Now we can do all of those because they're all the same idea. It's the sum of many slices. And the only difference is the slice parallel to the x-axis or the y-axis, and what kind of geometry are we looking at? There is a lot of geometry to this. It's good review. So, for these slices, now these slices are really thin, so thin. Now I understand the minute you go off that slice, really the base changed. But in calculus, the difference between this slice and the one next to it is microscopic. So we could really say it is the sum of many prisms, and they're so thin that both faces are all but the same. It would be like saying, you know, does this paper really have a different area on this side than this side? But so they're the same, all but the same, okay? So, the area of the base, that's going to depend on the geometry of the cross-section. Square, circle, triangle, semicircle, rectangle. Height, that will have to do with the thickness. And so that's going to be either dx or dy, depending on the problem. Now let's go there. Area of the base. What is the area of the base, formula-wise, geometry-wise, if the cross-sections are square? Just based on height or side squared, yeah? Do you agree? As far as the thickness, is that dx or dy? It's dx. Going side to side, so it's dx thick. Cool. All right. Now the side. How long is the side of the square? Well, these squares, this is why it's calculus. These squares aren't all the same side square. They're constantly changing. Every one of them is different. Infinitely many different sides. But every side ascribes to the function. What's the side? It's just root x. Each side is root x. And we square it because we're finding the area of the square. So root x, it's root x base times root x height. So the area of each face is just x. And from where to where? 0 to 4. So the area, the volume of this, though it looks really complicated, is just 8. All right. Now, this is pretty cool. If we had a 3D printer, this would be the perfect time for it, because this is really very much the idea of a 3D printer. It takes measurements in 3 space of an object. It starts saying, all right, how far is it? And it builds a ground layer slice, and then it goes up a little, and then takes measurements and talks about, all right, now what's the slice look like? And then it goes up a little and tries to duplicate another slice. And it's really just slice upon slice upon slice upon slice. Now, let's try this a little different. Reading carefully now, this reads almost the same. It says find the volume square cross sections. But the key idea is it's parallel to the x-axis. So when you go to draw your x-axis, and then your slanted y-axis, and then 1, 2, 3, 4 and x, and 1, 2 and y, parallel to the y-axis, same region. Are we cool? We're going to make slices parallel to the x-axis. So there's one. We kind of run out of room pretty fast, but like that, yeah? So these, because they're square, each of these heights will be exactly the same as the base. So if you were to connect the points, it kind of comes out of the back corner and is swelling, or like a tunnel. See? Okay. So let's talk volume. Volume is the sum of many area of the base times the heights. The area of the base is still side squared, but the height or the thickness of the slices is now dy. Here's the thickness here. It gradually changes as we go back. When I draw mini slices here, it's dy. All right, now, a little harder for the side. How long is each side of the square? Ooh, horizontal. I better be careful and use the skills I've been taught. Right minus left. Right is 4, and left is the square root function or y squared. Which one should I use? Y squared, because I'm integrating with respect to y. So each side is the whole distance to 4. Remove the distance to the curve. That leaves me with the distance between them, 4 minus y squared. From 0 to 4? 0 to 2. And then I put a pi out front, right? There's no pi here. Why not? They're not revolving. There's no disk. There's no pi. Okay? No pi. If you're putting pi in there, you're trying to memorize calculus rather than actually do calculus. Okay? It's like somebody who's trying to memorize a dance instead of just feeling it. You know what I mean? It's just awkward. Okay? Just feel it. You know? Okay. Now, let's try a different section. If we try a section that has, so draw your x-axis, normal, horizontal, y-axis at a slant, y equals x, or f of x equals x, is basically just splitting the region, yeah? Oh, darn it, I missed. So there's f. Should have done this in some different color. Oh well. And then g is negative x plus 4. So what's the y-intercept? 4. So go up 4 on the y-axis. And it's going to go down 1 over 1. But I got to tell you, slope's kind of hard to do on an angle. So I would personally do, oh shoot. I would personally do 4 units along the x-axis because one would have an x-intercept of 4 as well, if it's going down 1 over 1. So if you connect, what the heck is going on? Why do I have so many lines? There you go. If you connect the two, it might look like that. Now, am I talking the section with the x-axis or the y-axis? Read. Y-axis. So I'm talking this region, not the lower triangle region. It says the 2 curves or lines and the y-axis. All right, so that's the region. Now, how shall we draw our slices? Read. Parallel to the y-axis. So here's the y-axis. We're going to slice this way. Parallel to the y-axis. So slices go that way. All right, now the type of geometric figure, not squares anymore. Rectangular cross sections parallel to the y-axis with height half the base. So, for example, here, when the base of the rectangle is 4, the height is 2. So you should go up 2 in kind of z-axis direction. All right, and as the slices get smaller and smaller, the heights get smaller and smaller until they go to a point, yeah? As the distance between the 2 lines goes smaller, the height of the rectangles gets smaller as well. All right, very good. Okay, now let's talk the approach. Start general, area of the base times the height, and then get in the geometry and the differential. Is this dx or dy? X, and area of the base is just a rectangle, so base times height, yeah? Alrighty. Actually, might do a little more before I get to the curves. Before using the curves, do some more geometry. I think you'll be better off. I think the other class had trouble because they were in a rush to get the equations in there, and I think you'll find it easier if you do a little more. What do you know about the base and height? If the height is half the base, then couldn't I make the inside even cleaner by just calling it 1/2 base squared dx? You follow? All right, now we're rolling. Put the half out front, square, dx. What's the base of each rectangle? Are we talking right minus left or upper minus left? Upper minus lower. What's upper? What's lower? G of x minus f of x. I didn't find the intersection points, but maybe by guess and check you could tell me what we're talking 0 to 4 or 0 to something we don't know? 0 to 2. They meet at 2. Okay. And if we needed to set them equal to each other and solve, we could, but it's pretty obvious. So 0 to 2. Down? Try the next one, please, on your own. Yeah. Look through 2 curveballs at you. I hope you're reading carefully and being careful. Help each other, math amigos. Perpendicular to the y-axis is the same as parallel to the x-axis. So I hope you read that carefully. Any of these look like Chiefs? How we doing? Okay, yeah, so not first thing, but hopefully you saw, I'm going to need 2 integrals because I have 2 different right minus left situations. Cool, that's one gotcha to this. What's, the next is that it doesn't go to a point. That's weird, that's not like we were doing. That actually makes your life easier, not harder. So this first region, what's the base of every one? The base of these seems like it's constantly changing, but it's just right minus left, the distance to the y equals x line. Yes. But in y terms, so just y minus 0 or y times, what's the height of each? 2. It's always 2? Yeah, it's always 2. Y from where to where? 0 to 2, okay? And upper region, the right starts to become the other line. So what's the base of the upper section? Negative y plus 4, the line in y terms. What's the height of each slice? 2, and the limits to integration? 2 to 4. Okay, now, because this has two congruent bases, all the same distance from each other, we actually could do this with geometry. This one, not most of these, but in this case we could. What's the formula for that kind of figure? Area of the base times the height. Anytime there are two congruent bases, that's a prism. Prism is area of the base times the height. Now, are these, when I say area of the base times the height, am I referring to the slices anymore? Or am I saying the area of the base is the area of the actual building block base? So what is the area of the triangle down there? What's the base? 4. What's the height? 2. And what's the capital H height of the prism? 2. And so we get 8. That is what you get with the calculus. But the geometry in this case is probably really. Are you with me? Let's go to another idea or two. Triangles. Okay. The rectangle enclosed by these two curves. Let's draw the, not the rectangle, the region enclosed by these two curves. So f of x equals x squared. Give me an x-axis, a y-axis. Go to, I think, 2 in each direction in x. You do need to go into the second quadrant, and maybe 5 or 4 in the y. And so your parabola should look like that, or better. And your line goes like that. And so I get this region here off of which to build. You follow? Okay. While I'm thinking about it before I forget, I don't know if you saw this note, but women, if you're involved in interested in engineering, there's some really awesome lady coming from GE and the Society of Women Engineers. She's not just talking, I think you're building something, I don't know. So tomorrow, 7th hour into a little after school, and they're providing pizza and all this stuff. So if you're interested, come in. So the engineering didn't get you, oh, pizza, okay. There's a sign up on Miss Pruitt's door if you're interested. All right. Now back to this. Equilateral triangle cross sections. I'll come to the equilateral triangle. First do the slices. Parallel to the y-axis. Runs this way. 1 or 2 should be sufficient, although the picture looks cool. I don't know. You have to do what you think is right. So they're equilateral triangle cross sections. So out of each of those comes an equilateral triangle. And it would go to a point at both edges, so now it looks like cheese. Okay? It shouldn't be, I'm favoring too much to the right maybe, but hard to draw. Okay? Okay, now. Okay, so the volume is the sum of many prisms. For the area of the base, we'll talk about that, but what's the height, the x or the y? It's dx. Okay, so off to the side here, we're going to do a shortcut for equilateral triangles, but not yet here. All right, so you have choices. There are actually 3 ways to find the area of a triangle. What are they? Base times height divided by 2. Come on, you learned the other second one, not the third one, the second one. 1/2 AB sine C, and then, anybody know the third one? Yeah, Heron's formula, that's exactly right, Heron's formula. When you have three sides, you can use Heron's formula in the semi-perimeter. We don't teach it at our school, but it's a kind of handy one once in a while. Anyway, we're going to use, you're going to definitely want to use 1/2 AB sine C here. And let me explain why. Because it's equilateral, what do you know about A and B? They are the same. And what do you know about the angle between them? It's 60 degrees. And so in equilateral triangles, what's the sine of 60? Root 3 over 2. Combined with the 1/2, you can do root 3 over 4 of a squared dx or dy. So for equilateral triangles, use root 3 over 4 of a side squared d whatever. It could be dx or dy in this case. You with me? Limits of integration. I didn't find the intersection points, and I still have to put in for a. Will you just take my word for it that these meet at -2 and +1? Okay. So let's finish this up, at least setting it up. I don't know if we'll take the time to put in our calculator just because I want to make sure I get to everything. What's A? It's upper minus lower or right minus left? Upper minus lower. What's upper? G of x and lower? So a side would be G minus F squared for the area, and the root 3 over 3, 4 comes from there. Area of the base times size, or the 1/2 AB size. Are we good? Okay, this one is a little wackier. This tends to be one of the ones that coops students out more. Read carefully, but it does rely heavily on geometry skills. So you got your x and y axis. You got the same region, I believe this is. So find your parabola. Do the line. And you've got the region. Stripe the region with sections parallel to the y-axis again. So that's the same. All right, are we good? All right, now, here is the deal. The figure is isosceles right triangles with the hypotenuse and the plane of the base. That's a mouthful. So right triangle is easy. Isosceles implies the legs are equal. So that kind of figure, but it's got to be the hypotenuse. Oops. Okay. All right. Doesn't it feel like this should be rotating? All right. There we go. Okay. The hypotenuse in the leg of the base. All right, something like that. So you're going to draw triangles with the right triangle poking up, or the right angle poking up. And it looks something like that. You see? And the geometry is no walk in the park with your girlfriend. It takes skill. So area of the base times the height. The area of the base, we'll talk about in a minute. The height, dx or dy? Dy, dx. Which one? Dx. It's definitely dx. Okay. All right. Now, for this, I'm not sure. 1/2 AB sine C or base height divided by 2. Let's maybe draw a little cleaner figure without all the analytical geometry to it. I think you'll agree that this, the hypotenuse, is definitely what we're going to be able to find by virtue of the curves, right? Do you agree? This is known. All right. What else do we know because it's isosceles? What does that do for us? It makes these sides the same, cool, but what else does it make? And the angle's the same, so don't these have to be 45s, yeah? Okay, so I could figure out this guy's relationship to the base by some kind of trig or geometry, but I think it'll be easier to go here. What do you know about the height? Let me do some highlighting for you here, okay? Look at this triangle just on the left. What do you know about it? It also is a 45, 45, 90. And does it have some subcongruent sides or smaller congruent sides? Yeah, these guys have to be equal, yeah? Because this is 45 and this is a right angle drawn in an isosceles triangle, has to be, the height has to be at a right angle. So I've got a 45, 45, 90, so isn't the height equal to half the base? Cool. So if we use base height divided by 2, then trying to simplify this down, I could say this is base times half base divided by 2, or base squared over 4. See? All right, now let's get into further detail. The 1/4 I'll just throw out front. What squared? G of minus f, or upper minus lower. Limit still from -2 to 1. And throw pi in for no reason? No, that's ridiculous. Okay. Last but not least, doing good on time. Last concept, all right? The region enclosed by the sine curve x equal pi over 2 on the x-axis is the base of a solid. So give me a horizontal x-axis, a slanted y-axis. Find pi over 2 on the x-axis, fairly close to the end. And draw up at pi over 2 parallel to the y-axis until you get to the peak of your sinusoid. It looks cool to do the rest of it. Okay? You cool? All right. Now, the sections are parallel to the y-axis. You've got to read carefully. Sometimes they'll say parallel to the y-axis. Sometimes they'll say perpendicular to the x-axis. You got to read. Parallel to the y-axis looks like that's parallel to the x-axis. Parallel to the y-axis looks like this. Yeah. Okay. Now they are semicircular cross sections, so they'll look like this, this, that, and there's this kind of ridge going on. Semicircles or half circles. Okay, so into the volume we go. Volume is still the sum of any area of the base times the heights. Area of the base. What is it? Geometrically speaking. R squared over 2, and are we talking dx or dy here? Dx. All right. Now, that's a little cumbersome because the radius is bad. Radius is bad. The diameter is good. Because in terms of finding this distance, are we going to talk upper minus lower? And I don't want to do halving and all that stuff every time. We're going to do something a little cleaner. So can you agree that diameter is really what is closely related to the curves? Yes. All right, so we're going to take this to diameter term. What is the radius in terms of the diameter? The radius is twice the diameter or half the diameter? Half the diameter. All right. So if I do half the diameter and clean this up, then when you do semicircles, the shortcut is just to do pi over 8 of the square of the diameter. Okay, put that in a note box for semicircles. I didn't do one for isosceles because they really are different case by case, but for semicircles, you want to do pi over 8 of the diameter squared dx or dy, depending on the sizes. Okay? All right, now, pi over 8, cool. From where to where? 0 to pi over 2. What is the diameter? Just a function, minus 0, so just a function. Sine of x all squared. Could you do that without a calculator? Yes. Yeah, because you guys got crazy antiderivative skills, right? You know antiderivative of squared sine functions, power reduction identity, and all that stuff, yeah? So you could use it directly if you had to do that without a calculator. But let's move on to the last one. Try the last one on your own. Feel free to try it and punch it in your calculator if you have time, but at the very least, draw it and set up the interval. All right. This one is not as easy to integrate, I think you'll find. Are we ready? Ooh, that's a lot bigger than I thought. Did I do this right? Oh, I'm in degrees. I think like this. Calculus class. Okay, sorry. Did you get? That's very small. That's better. What'd you get? 0.448. Yes, indeed. What are the limits? 0 to pi over 2 or 0 to 1? 0 to 1. What's the diameter? Pi over 2 minus arc sine of y squared dy. And it is indeed 0.4483. Okay, cool. That, I think, should be as solid as you're going to get. You should be good. Just get work done on Friday and Monday. If you're having gaps, well, you're not busy, You good for myself or else? Go ahead, Mr. Murphy. Miss Demerit, she's a narrative. I wrote you as a. All right. Buenos dias.